Okay, in the second section, the first speaker is Professor Rafael LOPEZ. He is from the University of Granada in Spain. The title of his presentation, Translators of the Gauss Curvature Flow. If you are ready, Professor, you can share your screen.
Okay, thank you. But you need to give me...
Okay, yes, you are right. Okay, I think now is okay.
It's okay?
Yes,
okay.
We are seeing.
Okay, thank you. Well, first, I would like to thank to the organizer to give me the opportunity to participate here in this conference. The talk is a joint work with Muhittin Ebren Aydin from the University of Firat. I think this is Muhittin, sure. Also, there is a second work about translator in Minkowski space, but focusing only for rotational surfaces. Okay. I begin directly with the object in this talk is the study of surfaces in Euclidean space satisfying this equation. This equation is K is the Gauss curvature of the surface, N is the Gauss map, V is a fixed direction of the space.
Rafa, I think we cannot see the slides. Probably the same problem. Sorry. I see only the first page with the picture.
I don't know why.
It's okay.
It's okay?
Yes, it's okay now.
Okay. Well, okay. This is the equation to study. Okay. Then I repeat, K is the Gauss curvature, N is the Gauss map of the surface, V is a fixed direction, the name is speed, and alpha is a constant, is a non-zero constant. If alpha is 0, then here on the left-hand side is 1, then the surface satisfies that the Gauss map makes a constant angle with a fixed direction of the space, and these surfaces called constant angle surfaces. This is a different topic, okay? And then for people studying differential geometry, this is my case, then when we see this type of equation is a prescribing curvature equation, immediately the first idea is to find examples of surfaces satisfying this equation. Because if you have more examples, then I think the equation is more interesting. Okay. Sorry. The motivation to consider this equation comes from, essentially, from the Poincaré conjecture. When Perelman solved the Poincaré conjecture, he used an interesting tool to solve the problem. The problem is topological, okay? But he considered on the problem metric and curvature. And then he considered the evolution, in some sense, of the surfaces of the manifold along the time. And the idea is what topological property are preserved or not, okay? From the conjecture, many people consider other flow, not only about the Ricci flow, is this flow is used in the solution of the Poincaré conjecture, and also the mean curvature flow and the Gauss curvature flow. For the mean curvature flow, the idea is to consider a uniparametric family of surfaces satisfying this equation. This is the derivative with respect to the time, then is the mean curvature times the Gauss map at each point of the surface. And in the initial time, you consider you have a fixed surface. Okay. But from motivation physics, it's interesting to consider some special solution of this equation, of this evolution, exactly. The solution, the special solution is called soliton. I think the English translation is self-solution. What is the idea? The idea is this surface preserve the shape along the flow. And then because the shape is the same, then the t variable disappears. And then the soliton satisfies a equation without t, with the time t. In this case, there are three special solitons. Solitons that are preserved by translation of the space. I mean, if sigma satisfies the flow, then the translation also satisfies the same equation. And then in this case, the mean curvature satisfies this equation. The mean curvature is equal to the product of the Gauss map times v is the fixed direction of the space. And also, self-shrinker and self-expander, the idea is that the solutions are invariant by the dilatation of the space. Depends if t is negative or positive, then the surface satisfies some equation about the mean curvature. This is the equation. In my case, the flow is by the Gauss curvature. Exactly, it's by the powers of the Gauss curvature. Then here, I replace the mean curvature by K alpha, okay? I have to be honest, and for me it's difficult to study this problem. Essentially for me is by the variable t. For this reason, I prefer to consider solitons of the flow, okay? Why? Because you need a lot of tools to work with this kind of equation. For example, parabolic equation. And then, for example, for t equals 0, there is always solution of the flow, okay? At least for a small t around t equals 0. Also, it's necessary to consider maximum principle because along the flow, you have to compare two surfaces at different times. And then it's important that the surface along the flow are different in some sense, so the surfaces change along the flow, okay? And also to consider a priori estimate of elliptic equation, because here the Gauss curvature must be positive to consider the power, okay? And then when the Gauss curvature is positive, then the equation behind is of elliptic equation, is of elliptic type. When alpha is equal 1, then here is only the Gauss curvature. Okay, here there are always solutions. For other alpha, it's possible to extend the result from alpha equal 1. Okay, and also, of course, the equation depends on the value of alpha. In general, people can study a positive value of alpha. The literature is great, of course. this is, in some sense, this is the first paper about the Gauss curvature flow. The people, in some sense, are from Australia. It's Urbas, Andrews, and the school behind these guys. As I said, I prefer to consider solitons of the flow. Okay, then the idea is that we don't see the variable t, the time t. Okay, when the solitons are invariant by translation, then this is the equation of the surface. Okay, I repeat, k is the Gauss curvature, must be positive. Okay, then for this reason, all surfaces are convex. Okay, if you consider the no-parametric way to look this equation, then if you consider graph of a function u, then this is the equation. This equation is this one. Okay, and in this case, the speed is vertical. It's 0, 0, 1. Then, if you look, it's a difficult equation here. Is the determinant of the Hessian. Okay. Along the talk, there will be a special case is when alpha is equal 1/4. Why? Because if alpha is 1/4, then the denominator disappears in this case. Okay. For example, in this case, the equation is this equation. This equation is famous in partial differential equation. The name is Mons-Ampère. It's the determinant of the Hessian equal constant. But if you compare with other famous partial differential equation, for example, the minimal surface equation is different, and for me it's more difficult because for minimal surfaces, the equation is not linear, okay, but it's almost linear. In fact, the name is quasi-linear because here you can see that here appear uxx and here xy, yy, okay, is linear, almost linear, okay? But here is different because you are doing product of the second derivative. Okay. Then there are many problems that you can pose with the above prescribing Gauss curvature equation. For example, find a sample with a special geometry. Example, for example, of ruled surfaces, rotational surfaces, etc. Also about the Dirichlet problem. The Dirichlet problem is to solve this equation in some domain of the plane with some prescribed boundary value. And also, even in this case, about the Dirichlet problem, other interesting problem by the minimal surface theory is the Bernstein problem. The Bernstein problem is to ask if there are entire solution of the equation. Entire solution means that the solution is defined on the full, on the whole plane, okay? These problems are difficult in the, if you see the literature about the mean curvature flow is different. And there are results about this problem, the last two problems, because I repeat, for the mean curvature is in some sense is more easy to study the equation. If people like partial differential equation, the difference is when you solve the equation for the minimal surface equation, you only need see one estimate. I mean, estimate only until the gradient of the function u. But for the Mons-Ampère equation, you need C2 estimate. Estimate up to the second derivative of the function are more difficult. Okay, this is the organization of the talk. The idea is simple. The idea is to find a sample. Then first I consider rotational surfaces. After helicoidal surfaces, Other is to find example by separation of variable, and finally about rule surfaces. About rotational surfaces, not only because these surfaces have a lot of symmetry. The idea is that the prescribing Gauss curvature equation change to be from a partial differential equation to ordinary differential equation. And then, in general, when you impose initial condition, you have at least a local solution of the equation. Okay. One problem when you consider the problem about soliton of the Gauss curvature flow, the mean curvature flow, is about the speed vector. Okay. Of course, you have after a rigid motion of the space, you can fix the vector v. Okay, but if you consider the problem about surface of revolution, the axis has no relation, a principle, with the speed vector. Okay. Then the first result say that v must be parallel to the rotation axis. This is the proof is easy. This is the parametrization of the surface with respect to the z axis. In this case, v is arbitrary, of course. This is the Gauss map, and this is the equation of translator. Okay. V1, V2, V3 are the coordinates of v, and then I change this equation like a polynomial of trigonometric function sine cosine. A0, A1, A2 are functions of the variable r, and then this coefficient must be 0. Okay, this is the coefficient. Okay, and then from the last two equations, because f prime cannot be 0, because in that case f is constant, and then you obtain planes, and then the Gauss curvature is 0. It's not possible. The Gauss curvature is always positive. Okay. Then v1, v2 must be 0, and then this is the speed vector that is parallel to the rotation axis. Okay, and then this is the equation when the vector v is 0, 0, 1. Okay. The result, our result is that it's possible to integrate at least once this equation. For this, we introduce this function g, and then this equation is equivalent to this equation, and then it's possible to get a first integration of this equation. This is the integration depends on the parameter alpha. This alpha is 1/2. This is g2, in other way is this expression. Important is what about the domain of the solution of the equation, okay? And then from this equality, we obtain information about the domain, okay? For example, if alpha is 1/2, then r must be bigger than this number, okay? In the other case, when alpha is not 1/2, then this number must be positive, okay? And also, this expression must be positive. There are two conditions. Okay? And then, essentially, it's not necessary to study more here. This is the domain. This is the domain in all cases, depending on the constant alpha. Okay? When alpha is not in this interval, then the domain is a finite interval. Okay? If alpha is between 0 and /2, then the domain is an infinite interval of the real line. Here, we don't know if r goes to 0 or not, depend of the constant m. Okay? It means that it's possible that the surface does not intersect the rotation axis. Okay, then this is the theorem. This is the parametrization of a rotational translator. If this is the parametrization, then F is this integral. Of course, it's not possible to get an explicit solution of the equation, but at least we obtain a first integration. If you compare with other cases, for example, when the mean curvature is constant, it's similar. When the mean curvature is constant, then you obtain a first integration. Okay, okay, and this is the domain. Okay, and in this case, when the domain is a finite interval, then we know something about the behavior of the function f. When the derivative goes to the left end point, then the derivative goes to 0. It means that the tangent is horizontal. Okay, in the other endpoint goes to infinity. Okay. For example, when alpha is not in this interval, I repeat, the domain is a finite interval, previous result say that it's not possible to get entire graph. Okay, and then I mean our results are according with this kind of the result for more general, of course. When alpha is 1/4, I repeat, this is a special case, then it's possible to solve completely the question. And then we obtain explicit parametrization of the surface. Okay, and this is the parametrization of the surface, and f is this expression. Cm are constant. Okay. For example, when m is equal 1, okay, then f is a parabola, and the surface is a paraboloid. Here, I put some picture when alpha is 1/4, okay? In the brown color is the parabola, okay? And intersect, orthogonal, the rotation axis. When m is bigger 1, intersect the axis, but not rotation, but not orthogonal, okay? And when m is less than 1, the domain on the left-hand side of the interval is not 0. The surface does not intersect the rotation axis. One interesting problem is about when translator intersect the axis and also the intersection is of orthogonal type. This problem, you can consider, for example, if you consider surfaces with constant Gauss curvature, rotational constant Gauss curvature, and this problem is not trivial. You can see the solution in the books, but the rotational surfaces depend on some parameters, intersect or do not intersect the axis. Okay. I mean, even in the case of when the Gauss curvature is constant, the problem is not trivial. Okay. Our result say that for any alpha, there are solutions intersecting orthogonal the rotation axis. Okay. And even we obtain some behavior about the function f. Okay. And this is when alpha is in this interval. Okay. If you remember, the function f is defined in the real line. Okay. And then we know the behavior in the infinity is like a power. Okay. And when alpha is not in this interval, is defined in some finite interval. Okay. But here on the left endpoint is 0. Okay. Then the idea is to come back to the first integration of the surface of the equation, and then impose the condition that first intersect the rotation axis. It means that f is defined at r equals 0, and also that the intersection is orthogonal. It means that the first derivative is 0. Okay, and then it's possible to obtain solution. Exactly the constant of the integral m must be 1. Okay, the solution is C2 using the L'Hopital rule, and after by regularity, in fact, the function is C is smooth, okay? And the behavior in infinity is only to compute this limit when R goes to infinity and apply the L'Hopital rule. This is some picture when here is when alpha is 1/2, okay? In this case, the function is defined in R, this is infinity, and when alpha is 1, is finite, the domain. In this case, when the surface intersects the rotation axis, it's possible to obtain a explicit solution for other constant alpha, okay? For example, when here there are some examples, for us, it was curious because we thought that only in the case 1/4 is the special case, but when other cases also is possible to complete, to solve completely the equation, okay? I repeat, all functions are convex because the Gauss curvature must be positive. The second step is the study of helicoidal surfaces. This is the parametrization of the surface. H is the pitch of the surface. The rotation axis is the z axis. Okay. And then this is the Gauss map. D is this expression. Okay. Of course, the equation is more complicated. And again, the first question is about the relation between the speed and the rotation axis of the surface. And then it's the same that in the rotation case, the axis must be parallel to the speed, okay? And then in this equation, V1 and V2 is 0. Okay, and then this is the equation, and also it's possible to get a first integration of the equation. Now I introduce this function. This function is exactly D. Exactly D. And then we obtain a first integral of the equation, and then with this equation we can study the domain of the solution. Okay. Here there are some pictures about the profile curve. Okay. Also here in this case, in depend of alpha, the function is defined on finite interval or not. Okay. And also here some pictures of the helicoidal surfaces. The third type of example is to find example by separation of variables. The idea is, okay, the equation is of partial differential type. It's difficult to solve, okay? But we try to solve the function like the sum of one function depend of x plus other function depend of y, okay? Then in this case, the partial differential equation change to be an ordinary differential equation, and then it's possible to solve, or at least it's easier, okay? This is the idea. For example, in the theory of differential equation, typical is to consider the product of two functions of one variable, okay? But also from the geometric viewpoint, this kind of surfaces has a special property. If this is the parametrization of the surface, then the surface is the sum of two planar curves, okay? Or even the curve are included in orthogonal planes, okay? And then there is many investigation about surfaces that can write like the sum of two curves, okay? And imposing some condition about the curvature of the surface, okay? Then our results are the following. When alpha is 1/4, remember it's a special case because all denominators are cancelled, then the parametrization of the surface is the following. we can change the role of f and g, okay? Then f is a polynomial of degree of 2 degree, okay? It's a parabola, okay? And the speed is, if it's 0, 0, 1, then I obtain this solution for g is also a parabola, okay? Or if b is 0, 1, b3, this is the expression of g, okay? This is, here, I repeat, the role of f and g interchange. If f is like this, then the first coordinate of the speed is 0, okay? If you fix g, then is the second coordinate of b is 0. But b is, in some sense, is more arbitrary than in the rotational case, because in the rotational case, the v must be parallel to the rotation axis. Okay. The proof is not difficult. You write the equation of the translator. Okay. And then there are two cases. The case is when the second derivative of f is constant, then f is a parabola, okay? And then you put here, and then this is the equation, and then you can solve completely, okay? If the second derivative is not constant, okay, and then for interchanging the role, the second derivative of g is not constant, then after some differentiation in this equation, you obtain this equation. Is f prime 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 three times, g 3 times is equal 0. Okay? If at some point of x, this function is not 0, then this function is 0, and then g prime prime is constant, then is the previous case. Okay? And if this number is not, if this number is 0, then you have the previous case. Okay? I mean, this case is not possible. Okay, this is the case when alpha is 1/4. Okay, then I put some example about in this case, because usually if I come back to the equation, okay, because the surface is a graph on the xy plane, then people think that is the best option to choose v is 0, 0, 1, orthogonal to the plane xy, to xy plane, okay? But there are more examples. This is the idea. And then I put here another example. This example is, okay. And then I change the coordinate. I prefer to choose v 0, 0, 1. And then here I put the function f and g depend of x and z variable. Okay. And then if you remember, f is control, and this is the equation of g. Okay. This is the equation of the surface. In this case, the vector v is not orthogonal to the plane where the surface is a graph. Okay, when alpha is not 1/4, the result, our result say that there are no examples. There are no examples, okay? Why? Because if you put the equation of the translator, okay, this is the equation. Then I do differentiation with respect to x, with respect to y, etc. Okay, with respect to x, this is the equation. P is depend of f and j. Okay, and after organizing this equation, I obtain a equation when appear coefficient depend of x is 0, is 1, is 2, is 3, and also appear a polynomial of g prime, okay? And then necessarily the coefficient must be equal 0, okay? And then when you consider coefficient by coefficient, study each coefficient, then you obtain contradiction. This is the idea of the proof. Okay, motivated by the theory of ordinary differential equation, is possible to study other type of separation of variables. In fact, this is the idea in the theory of ordinary differential equation. It's the product of function f and j. Okay, and then it's not necessary to read line by line this slide, but the key is that it's possible to obtain solution of the equation. Here, the parameter alpha is 1/4. Okay, it's true that this parameter is special. Okay, and you obtain a solution. Probably when alpha is not this number, the idea is that there are no solutions because the equation is more difficult. Sorry, no more difficult. The conditions are stronger. Okay, and then it's difficult to find example. Okay, but in this case, it's possible to obtain explicit solution when is the product of two functions. Okay, I prefer to skip this part. Okay, and then the final part is the study of rule surfaces. Okay, then the theorem says that there are no examples. There are no examples. If you remember, if people immediately before to continue, if you remember, for rule surfaces, the Gauss curvature is not positive. And then, because I am considering power of the Gauss curvature, then because k is negative, then alpha is not arbitrary. It must be to be an integer number. Okay. Okay. Then I consider this is the parameterization of the rule surface. Okay. And then the rule cannot be parallel. You see, the surface cannot be cylindrical because in this case, the Gauss curvature is 0. Okay. And then for this reason, I change the curve gamma to be the Strisian curve, some condition. Okay, and then this is the Gauss curvature, is negative. Okay, this is classical formula in differential geometry. Okay, alpha is an integer number. And now, after the computation of the Gauss map, this is the equation of the surface. Okay. And then after some manipulation, this is the equation. And then if you look here, appear function depend of t, this function. The coefficient depend of s, okay? And then I consider the Brownian of the three functions, okay? And this is the Brownian, okay? Remember that alpha is integer, okay? Then this number is not 0. Okay, then because t is arbitrary, okay, this number cannot be 0, and then this is a contradiction because here we have a relation of the three functions, and then you obtain a contradiction. This is the idea of the proof. Okay, and to finish, we consider the same problem in Lorentz-Minkowski space. Probably people like this space. Here there are many types of situations because the surface must be space-like, time-like, okay? Also about the speed v also depend of this function, of this vector. Probably the problem change. Okay, for this reason we prefer to study only rotational surfaces. Okay, and then because in this case the equation is an ordinary differential equation, then it's more it's easier to study in some sense the equation. Okay, when I consider a space-like surfaces, then there are not surfaces intersecting orthogonally the rotation axis. In this case, it's curious because if you compare with the Euclidean case, you obtain for any case of alpha surfaces orthogonal to the rotation axis. Okay. In some cases, the intersection is conical. I mean that the tangent plane is of light-like type. Okay. If I consider time-like surfaces, then I write depending on the case. Depending on the case is because there are two types of parametrization of the surface. Then in some cases, there are no examples intersecting orthogonally the axis, but for other parametrization, there are examples. Okay. And in this special case, when alpha is 1/4, you remember it's special because the equation simplified a lot. In some sense, almost denominator disappear. Then you obtain explicit parametrization of the surface. Okay. And I think that this is all. Thank you.
Okay, thank you, Professor Lopez, for your nice presentation. Is there anyone who wants to ask a question or any comments? I think there is no one. Maybe Professor Muhittin Evren wants to say something. If he wants to say something, you can raise his hand. Okay.
I'm sorry, do you hear me?
Yes, we can hear you.
Okay, thank you very much for giving a chance to say something. And I want to thank the Rafael for the nice conference. And I must say that I always learn new things when I listen to Rafael. Okay, that's all I want to say. Thank you very much. And also, thank you for this nice organization. Okay.
Thank you, Professor Aydın,
Welcome.
for your
Thank you.
comments.
Thank you too.
Okay. I think the speech is end now. Again, we have a 15 minutes for a break. After the break, we will continue with the Professor Ferda Kahraman Aksoyak. Thank you again, Professor Lopez, for accepting our invitations.
Thank you.
Thank you, Professor.